How's it going? Just making a quick video about this vibration table I've been working on. See, I saw some stuff online about other people making vibration tables with speakers, but yeah, I guess my particular thing is I want to be able to replicate some like known vibration standards, and like ultimately I want to mount electronics onto it, and sort of just run them through tests and make sure that they can survive certain levels of vibration and stuff. So I got this subwoofer in Halfords. It's actually designed to go in the back of the car. Like normally this surface here would be flat against the ground in the boot of a car, but yeah, I added some like wooden struts to it so it can stand upright. And yeah, basically what I've done is I've added a screen here which has a Raspberry Pi on the back. It's kind of hard to see there, but it's just a Pi 3B plus, and then I have a cable going to this sensor on the actual table, which is just an accelerometer, and that can measure up to like crazy high amount of G's, like 500 G's, because yeah, I wasn't really sure how high of a G level I'd be able to actually hit with this table, so I just sort of got a sensor that could go very high, and it turns out, I'll show you later in the video, but it's like, you know, I could sort of hit about 15 G's at certain points. So yeah, it seems like that's the max for this table. But yeah, so it does consume quite a bit of power. So I've got mains coming in. This is like a 3D printed mount for the mains plug, and then I've got this is a 12 volt DC out converter. So it's like roughly, I think it's a 600 watt unit. And then this is just a DC-DC converter for the Raspberry Pi. And then yeah, so the Pi cables go straight into the Pi, and then the 12 volt for the speaker comes across into this panel. So this is just like, basically it's a subwoofer with an integrated amplifier, and the cool thing about it is you can just literally yeah, so what I'm doing is on the Raspberry Pi it has a 3.5mm audio output jack, and that's literally just gets fed straight in to the audio in of the amplifier here. So yeah, that's basically all there is in the actual physical setup of it. It's fairly straightforward. The cool thing about using the audio out jack, basically it means that you can just use like Python on the Raspberry Pi, and there's loads of libraries for like writing to the audio buffer. Like there's a library called Pi Audio, which is what I'm using, and I actually use ChatGPT to write a lot of this stuff. So this is just a simple GUI. So right now you can see I've got it going at 3 Hertz, so you can see it sort of going up and down there. Oh yeah, so I forgot to actually talk about the table. So yeah, you've got these cones, obviously the subwoofer cones, and I've got these 3D printed mounts that actually they mate to the cones, and they were epoxied on. And then on top of the 2 cones, they actually give me like, there's bolt holes on each of the mounts there, and so that let me actually screw this table down, you know, so the whole thing is sort of solid. And I was worried I was going to break the glue seals, but I used a really strong epoxy, and I like cured it for 24 hours or longer actually. So far it's been fine, but I'm going to do some extended tests on it, so hopefully nothing snaps off. But yeah, back to the GUI. Basically, yeah, it's just a real basic GUI. I can change amplitude, frequency, and I can run for a certain amount of time. So yeah, it's kind of interesting to see how high I can get things to go. So yeah, if I change the frequency here, yeah, so there is 27 Hertz. It's kind of hard to see, that's why I put the glove on. And you can see here, you know, if I increase this, if I increase the amplitude, so yeah, the amplitude goes between 0 and 1, but if I go up to 1, you know, at this frequency I can hit about 5 G's. Yeah, so I'm reading the G's here as well, I forgot to say that. But yeah, so, and if I change frequency, and yeah, I'll stop that there, it's a bit much. But yeah, so what I'm finding is basically the table has a frequency response. So obviously, you know, if I just leave the amplitude at 1 and sweep the frequency, I don't get a constant level of G's all the way through the frequency range. And especially as this is like a subwoofer, as I get into the over a couple of hundred hertz, like over 200 hertz, you know, the frequency response just drops way off. So yeah, what I want to do is I have like a manual control GUI here, but I want to actually write a control script that it'll have a control loop, and basically it'll be able to sweep over a certain frequency range and be able to set the G level throughout that range. So it'll have to control the amplitude being sent from the pi and monitor feedback from the accelerometer, and do all that control stuff. So yeah, I'm gonna basically spend a couple of days working on this, and we'll see if we can get something going. Alright, so I've written a script that will basically read out the G level in real time on my computer here, and then on the Raspberry Pi, written a script that'll sweep from 10 to 300 hertz at max amplitude, so we can see what the table can actually do and see what the frequency response is. So we'll start the script here. I can check the graph. Cool. And actually, my script starts coming back down again, but yeah, no need to check that. So yeah, that's pretty interesting. So that's the frequency response of the table. Yeah, it does have peaks, obviously. So it just means that whatever control script I write, like let's say for example, I want 5 Gs all the way up to 150 hertz or whatever. It just means that my control algorithm is going to have to be able to handle those resonant points, and you know, output a lower output accordingly. So yeah, I'm gonna have a play around now with some PID loops and see how I get on, and I'll update you with how that goes. What I've decided to try and go for is in this document called MIL 202, which was actually written by the Department of Defense. It just specifies a load of standards for like testing of electronic components. So it's pretty handy for me because I'm just looking for something to try and replicate, and this one's pretty easy to use. So this one is called Method 201A. Go from 10 to 55 and back down to 10, and you gotta keep the vertical displacement at 0.06. Yeah, some of these standards actually specify like the vertical displacement, so you can actually convert from that back to G. So that's all I've done, and what it works out at is basically at 10 hertz I'm at roughly 1 G, then at 55 hertz I'm at 9 Gs, and I go linear between them, so I vary from 1 up to 9 linearly with frequency, and then I go from 55 back down to 10. So yeah, I've got the controller set up. I'm just going to run this now. So yeah, on the graph, basically the green line is the actual measured G level, and then the blue line is the set point. So we should see as the set point rises, my controller, PID controller, will try and keep G on the blue line, but we'll see how well it does. Okay, now we're coming back down from 55 back down to 10. Alright, so I mean, it's not perfect by any means, but it's pretty good. Like, it don't need it to be absolutely bang on. I mean, for what I want, it's going to do the job just fine. So I'm going to leave it there. And yeah, maybe if I do some more cooler stuff with it in the future, I'll let you know. But yeah, I just wanted to make a quick video documenting what I've done so far. And yeah, I'll leave it there. See you.